All right, everybody, I think we'll get started. So thanks for coming in person or online to the first Marine Science Seminar for the fall semester. We have a nice lineup of 8 or 9 talks throughout the semester, so it won't be every Friday, but there's usually 2 a month. And we'll be doing it hybrid, so we'll have a lot of in-person speakers throughout the semester. And I think we have 1 or 2 that are virtual like today, but I'll always set it up in person if you want to come over and see other people. And we do have coffee and pastries here for anybody that might be in their office at Stennis and wants to help us eat them. So I will introduce our guest speaker today, Dr. Nabi Allahdadi. He is a research scholar at North Carolina State University, and his research field is in wave modeling and coastal physical oceanography. He has a background in hydraulics and civil engineering with some degrees from Iran, and he did his PhD at LSU, graduating in 2015, working on numerical experiments of hurricane impact on vertical mixing and destratification on the Louisiana shelf, so waters close by to us. And today he's going to tell us about several different U.S. coastal areas in the wave modeling that he's been doing. So we're very happy to have him today. And when we get to questions, for online people, you can just go ahead and raise your hand, and we'll manage those. All right. So go ahead, Nabi.
Oh, sorry, I was muted. Thank you very much. Can you hear me?
Yes, we can.
All right. Thank you, Chris, and thank you all for attending this seminar. I should appreciate University of Southern Mississippi to give me the opportunity to present our research here. It's a pleasure to present this research today. So this research is actually on the work that we did during the last 6 years at NCSU for preparing high resolution models for characterizing wave energy along the US coast. This research is supported by Sandia National Laboratory, and here I should acknowledge my co-authors, Dr. Ruing He from NCSU and Dr. Vincent Nieri from Sandia National Lab as the financial supporter of this project. So let me see if I can go to the next slide. Yeah, just I should wait. Yeah, please just give me a minute. See what's going on. Doesn't go to the next slide. I don't know why. Okay, now it's good. Okay, sorry for that. So the motivation for this work is actually the known problem of climate change and global warming, that we are always looking for alternative forms of renewable energy to get rid of the fossil fuels and tackle this problem. Wave energy is always a good alternative because it's always available. The waves are always in different forms are available in the ocean, and we can extract wave energy using the wave energy converter or WEC as we use here. So the coastal waters of the US coastal shelf waters include about 10% of the global wave energy. The figure on the right, this is based on the modeling that APRA did in 2011, and they prepared a map of average available wave energy along the US coast, on the West Coast and East Coast and the Gulf Coast. As you see, the West Coast is contains much larger energy potential for extracting, but still we can use the coastal areas on the in the Gulf Coast and on the East Coast to extract wave energy. So, but we need more detailed study for this characterization. These characterization studies can be used for finding hotspots, the areas with larger energy contains, or the areas with easier energy extraction, and also to determine some more detailed parameters that are used in engineering design of these wave energy converters or VECs. So these figures actually show some schematics of how the wave energy converter looks like. So on the upper left panel, we have a schematic of a wave energy converter as a floater across the water column, and it's moored using the mooring. It's connected to the seabed, and then the wave comes from the left side and propagates from the left side, oscillates the floaters, and this mechanical energy is converted to the electrical energy using the uh, electrical chips inside the instrument, and then it's actually transferred to the main station or the coast. So, and on the right is another figure that shows how the wave energy converter, which is on the very right part of the figure, is connected to the buoy, and the mooring on the ground. The lower left panel shows the specific engineering design of wave converters, how it looks like. And on the right, we have a kind of a lab model, which is a smaller scale that is used for laboratory tests and to find specifications of this kind of instrument. So, also the wave energy converters are usually used as an array, like hundreds of them in a specific area as a wind farm with specific distance in both directions, and then they are connected together using some cable, and these cables are connected to the main station to again transfer the energy, mechanical energy that is transferred to electrical energy. So I'm not much of wave energy converter engineer, so these are just some opening statements to see why we need to do this wave energy characterization as the end application. So this figure shows that how we start and why we do wave energy characterization. We start on the upper left from the WEC facilities, and then for locating the hotspots and finding the engineering parameters for designing these facilities, we need some parameters. In the table, we have 6 parameters specified by standards like IEC 2015. These 6 parameters, I will show you in a minute in detail. They are actually calculated, all of them are calculated based on the 2D spectra. And the 2D spectra, 2D wave spectra, is a kind of digital table array with rows and columns according to the number of directional and number of frequency bands. And this data is can be achieved using a model, a spectral model, either high resolution or low resolution model. For this simulation, we use a high resolution model. So these are the 6 parameters that I was talking about. IEC parameters. IEC is a standard for energy characterization. We used the version in 2015, and these 6 parameters, including significant wave height, energy period, omnidirectional or unidirectional wave power, spectral width, directional maximum power, and directionality coefficients are all calculated based on the spectral moments. And the spectral moments is actually integration of wave spectrum, which is S in this slide, within the frequency and directional space. So back to our model. Our main objective was first preparing long-term modeling database for waves that are used for energy characterization for different areas like East Coast, Gulf Coast, Puerto Rico, and US Virgin Islands, using a high-resolution model. The high-resolution model is a kind of important, crucial here, because Department of Energy wanted to make sure that no scale effect degrades the model accuracy. So, and then the other goal or objective of this study was using all those 6 parameters that IEC presented to calibrate and verify the model, because all the previous models were just relied on verification based on wave height and period, and not the rest of 4 parameters that are specifically designed for wave energy converters. And also the last one is presenting these 6 IEC parameters over the modeling area in the form of 2D maps, time series, and also partition spectra that is vital for designing these the wave energy converters. So our model, some general model configurations. We use SWAN, and based on the structured mesh, this was a kind of the thing that give us more flexibility than structured mesh with complicated coastal areas. And the coastal resolution was 200 meters within 20 kilometers from the shoreline. We use CFSR wind field, boundary conditions from the global wave stream model, length of simulation 32 years, and 2 models. As I mentioned, there were actually 2 different phases. We started the project 2016 with the East Coast, and then continued after 2018 with the Gulf Coast and Puerto Rico and US Virgin Islands. And the outputs, there are some specific outputs for this project. We need IEC parameters over the modeling area, over the mesh grids within the EEZ or exclusive energy exclusive zone area, partitioned wave parameters along the specific contour lines, and also 2D spectra at selected locations. So these are some general tips about the SWAN model that we use in this simulation. I'm not going to bother you with details of the model equations, but this is a kind of spectral model working based on the conservation of wave action energy, wave action. So on the left we have transport. On the left of the equation we have the transport terms, and on the right we have the source terms. The source terms include source and sink terms, in this case, wind wave generation, wave breaking, and bottom dissipation, and nonlinear wave interaction. The wind wave generation actually itself includes wind generation and generation by wind and the white capping that it's crucial for our model verification that I will talk about that later. So starting with our mesh generation, we had a huge mesh for first for the East Coast. Our East Coast mesh actually includes more than 4,300,000 grid points, or roughly 4,400,000 grid points. Resolution again was 20 kilometers within the 200 meters within 20 kilometers of the shoreline, and the resolution along the offshore boundaries was 10 to 15 kilometers. But here, from left to right, we have a map of mesh resolution with the focus on the coastal area. And then the mesh itself, it's almost black everywhere because mesh is very fine. So we have some actually zoom in area, a closer view in the Gulf of Maine and in the southern Atlantic bight that shows that we have a very fine mesh along the coastline. This is the same for the Gulf Coast and for Puerto Rico Virgin Islands model. So again, we use the same high resolution model. For this mesh, we have more than 5,700,000 grid points. It is a huge mesh. So, and then again, we have some close views for Puerto Rico and Virgin Island area and the area around the Tampa Bay. So, and these two figures actually they show the two different view of the mesh resolution maps. So the data that we use for setting up the model for offshore area, we used lower resolution data eTopo1 model with 1600 to 1800 meters resolution. But for the area closer to the coast and for the inner shell area, we use the other NOAA, which is coastal relief model, and the spatial resolution of this model is 80 to 90 meters. We use CFSR wind data. Later, I will show you that we actually verified this with other models, check to see if this is the best model or not. But this model actually, for the East Coast, for example, it showed in January, it showed the outbreak of nor'easters, and in July, summer, both July and January showed the trade winds in lower latitudes, and also the seasonality of wind throughout the year is clear based on this data. Also for the Gulf Coast model, these data, we consider different options when we are calibrating or verifying the model. But for these models, we have two, for this area, we have two specific distinct atmospheric features. One of them on the left is the hurricanes, that here for 2008, we have Hurricane Ike and Gustav, and also the cold front outbreak that we start from September, and we have them kind of continuously every week or 10 days by maybe early May. So for model verification, we used mostly NDBC buoys, 18 NDBC buoys for the East Coast model, and more than that, 28 NDBC buoys for the Gulf Coast model, or GP or VI as we say here. Also 4 CDIP buoys and 2 WaveSeas buoys over the Louisiana Shell. We use CSI 6 and CSI 9 for people who are familiar with that, with those stations. As a boundary condition, You see, we have long boundary conditions for the East Coast model on the left and the Gulf Coast model on the right. We used wave sheet data. These wave sheet data were taken from the global model with spatial resolution of 0.5 degree with temporal resolution of 3 hours. They were actually prepared based on ST4 physics package, which is one of the modern physics package in the in wave sheet. So wave height, peak period, and wave direction were forced to the model boundaries. This slide shows a kind of verification that we used for the input data. On the left, for wind, we compared the wind from CFSR, from the wind from buoys, and also the wind from another source in the lower panel, NAR data, that shows that obviously CFSR provides a higher accuracy of wind for this modeling, and this was pretty much the same or similar in other stations. But these kind of differences can be and was used for interpretation of the results later. And on the right, we verified the wave sheet data that we use for the boundary condition. So close to the boundary, this one is an example for the east for the Gulf Coast model. So as you see, for wave height HS, we have a good agreement. It is consistent with all the papers, all the modelings, the kind of classic accuracy. But for peak period TP, the accuracy is sorry, excuse me. The accuracy is smaller, and this was actually used later again for interpretation of the results for the areas that were close to the boundary. I mean, for this model, we consider the boundary as far as possible to our modeling area, but still it can affect the Puerto Rico and Virgin Island area of this accuracy. So we started our modeling with sensitivity analysis. There are lots of parameters in SWAN models that we cannot just use the default or just pick something based on some recommendations in papers. Lots of them are site specific, and we need to do sensitivity analysis for a specific geographical region or specific wave climate. So these parameters include computation time step, number of iterations, the way that we resolve the boundary condition, and also number of spectral frequencies and number of spectral directions. So specifically, these two first rows, computation time step and number of iterations, are very important to be considered in the framework of sensitivity analysis. The reason is in SWAN, although the model is based on an implicit scheme and there is no Coron number limitation, at least based on the stability, but there is actually a Coron number limitation. And that happens when the large Coron number increase the accuracy. So these two parameters, computation time step and number of iterations, they have a kind of interplay. So for a very small mesh, like 200 meters resolution, you will see in the next slide that we needed to go down to like 1 minute of time step. I mean, the most popular time step that is used in SWAN simulation is 10 minutes, but 10 minutes didn't work for our simulation. And so when we use a small time step, like 1 minute, the cost is the simulation time, lots of simulation time and resource need. So in order to increase the time to like 3 minutes, we could use the interplay between the time step and computational, the number of iterations. So instead of using a time step of 1 minute, that was the best, we used 3 minutes, but increase the number of iterations. These could save us lots of computational time with keeping almost the same accuracy as 1 minute. So sorry. So in this figure on the upper left panel, as you see, during the peak of hurricane, we ran the model with different time steps. So when the time step actually increased from like 5 minutes, we have significant shift of shifts of the peak, the time that the peak happens, and also decreasing. So we concluded that we need to use time step 5 minutes, preferably 3, 2, or 1 minute, or even 30 seconds. But that's computationally impossible or very expensive. So we used step of 3 minutes, but we increased the default iteration in so on from 1 to 3. So as you see on the right upper panel, for number of computational iterations, the result for iteration 3 and 1 were very similar. So we could do this kind of exchange to optimize our model. So also we had the sensitivity for number of spectral frequencies, lower left, and number of spectral directions. Not much about spectral frequencies. The default number that we use, 28, is working pretty good with not lots of sensitivity, but it's not the case for number of spectral directions. Actually, running the model with different numbers of spectral directions showed that we could use number of 24 for number of spectral directions, but this causes another problem. This small number causes another problem, that is garden sprinkling effect. So the garden sprinkling effect is a kind of spurious disintegration of continuous waves, mostly swells, when they propagate within a long distance. And because of the low directional resolution, they start showing these continuous funky patterns. And that can affect actually the accuracy of the model and change the simulation results. So the solution for that, there are two solutions. The first solution is increasing the number of increasing the directional resolution, or increasing the number of directional bins in the model. And the other one is adding diffusion term to the numerical scheme. Adding diffusion term to the numerical scheme, we tried that for many cases. It can improve that pattern, that funky pattern, but for 32 year simulations, there is no guarantee that it always works, because it causes instability. We are adding diffusion to the model, and diffusion is a kind of thing that make instability in the model. So we had to go back to the increasing the number of directional resolution, the number of directional bins. So based on the sensitivity analysis, we found out that 24 is okay with number of directional bins, but we had to increase that to 36. So these results actually are snapshots of this garden sprinkling effect caused by a hurricane in the Gulf of Mexico. Probably it's Gustav. Yeah, Ike. with different numbers of directional beams, 24, 36, and 72. 72 is very expensive. I mean, it significantly increases the model simulation time. But if you look at the 24 and 36, we see that we have a pretty good continuous wave pattern in the area that is actually affected by the Gardner sprinkling effect. So we chose 36. I mean, it's not just based on this example. There were lots of hurricanes and other cases were examined to get to the 36. All right. So after finalizing some of the parameters, or at least picking some of the model parameters based on the sensitivity, we started the calibration verification of the model. The metric that we use for the calibration are listed on the right. All those four parameters that most of the similar studies they use are, I mean, correlation coefficient, bias, RMSE, and scatter index. On the left, again, we listed those 6 IAC parameters. So the comparison between the model and the buoy was done between, for all these 6 parameters. So we have wave height from the buoy, but the rest of the parameters were calculated using the 2D spectra provided by NDVC buoys. And we use actually a code, a MATLAB code prepared by Sandia Lab to apply that. So before starting the calibration of the model, we just wanted to make sure that we are using the right white capping model. In the right white capping model, in Swan, the version that we use actually, and now we have also ST6 in the model, but at the time, 3 white capping, general white capping models, including Common, Jensen, and Westhuizen were available. So we first did some test simulation with default parameters of each of these models, and we calculated all of those metrics for the model, and we found out that the Janssen 1991 produces results actually the lowest errors, I mean scatter index, bias, and root mean square error, and the highest, almost pretty much the highest correlation coefficient. So we picked this one as the one that the white capping scheme that we were supposed to go forward with the more calibration and verification in the row. So picking the Janssen has 2 parameters, including C, CDS, and delta as the white capping parameters, and delta is actually the parameters that controls the high frequency fate of the spectrum. We use many cases. These are just some selected cases I showed here, but we use much more cases of the different couples of CDS and delta. We ran the model with each of them, and then we prepared all of these metrics at the location of different buoys. These values are actually the average for all the buoys, all those 28 plus 4 buoys that we used in our modeling area. So, and based on this simulation, we found out that the highest R and the lowest SI, bias, and RMSE generally is okay. Now two case actually appeared. We found out that we need to use a larger white capping coefficient during the hurricanes because we overestimated peak of wave heights, during the hurricanes. So CDS 3.7, delta 0.9 during the hurricanes, and during the non-hurricane times like cold fronts or fair weather conditions, to CDS 2.5 and delta 0.9 were the final white capping parameters in the model. These are some comparison that we did after calibrating the model. This is an independent time period that is not included in the calibration. So we have different IEC parameters, including wave height and energy period. On the right, we have epsilon or spectral width and theta max and D that we compared with the output, with the observation value that we got from the 2D spectra from the buoy. So, and this is actually the same, but the scatter plots that we got based on this time series comparisons. So, okay. The rest of the model verification includes that for different buoys over the simulation period, simulation area, and for a specific time slot, we used the data to calculate correlation coefficient and root mean square error and other parameters at the location of different buoys. So the color, this spot actually shows the location of one of the buoys, and the color shows the value corresponding to each buoy. For example, on the left, for the wave height correlation coefficient north of the Puerto Rico, we have something like 0.9 or a little bit more as a correlation coefficient. And then we have similar but for scatter index and the bias. So on the right, we see that the bias of the simulated wave height during this period is actually, most of the time less than maybe 0.1 meter, which is a reasonable comparison. So next slide, let me. All right. So again, more comparison this time between the simulated and observed 2D spectra for two stations, NDVC 42003 and NDVC 42036. That shows that generally the directional spreading of the spectra are similar, and we have a kind of similar frequency band between those. There are some differences that we can justify based on the type of the data or white capping wind input model that we use. So this table actually shows the final setup that we used for our Gulf of Mexico model. We have a similar one for the East Coast model, but pretty much similar to this one, but this is for the Gulf of Mexico model. So, as I mentioned, we use two different sets of the white capping, and we use Jensen as the wind input and white capping model, 36 for number of spectral directions, 28 for number of frequencies, and the rest of the details that I'm not going to go through. So for the production run, which was the big chunk of the work after sensitivity analysis, calibration and verification, finalizing the model output, we need to go for the production run, running the model for like 32 years. The mesh, as you saw, were huge, between 4 to 5, 6 million grid points. So we use high performance computing using the SkyBridge cluster in Sandia Lab. We use 600 to 1200 processors for running the model. This figure just shows an example for like 90 processors, how the domain decomposition work, work for over the East Coast, and each of these actually subdomains you see in the model, they have almost the same numbers of grade points. So characterization results actually, these data, the 32-year simulation results were used for characterizing wave energy along over these areas. The figure on the left shows the average wave power, or non-directional wave energy, over the 32 years of the simulation that we did along the East Coast. As you see, I mean, for latitude larger than 34, we have larger wave energy up to 35 kilowatt per meter in the offshore. But on the coastal side, we have something like 20 or less. And the panels B, C, and D, based on the characterization results, they are showing that the panel B shows again the wave power along the East Coast from latitude of 24 to like 45 along the East Coast, and along the line, different lines with different distances from the coastline. For example, the black line is along the line with a distance of 5 kilometers from the coastline. And we have the same for wave height. This kind of result can show us that at specific distances from the coastline in each latitude, we have what situation based on wave energy. The same plots were actually prepared for other parameters like energy period or spectral width, that will show how we can pick them and how classify the shoreline. So this figure shows the result of the classification. So for the classification result, based on the 32 years of simulation and different parameters, we classified the eastern coast of the United States to 8 zones, from ER1 to ER8. And each of them have their specific long-term attributes. For example, if you look at the J in the table, J, the first row, those two blue values shows the most desirable values. They are the maximum values because we have large amounts of potential wave energy. So region 3 and region 5 are definitely the area of interest based on the wave energy. So based on for example, seasonal variability, that I didn't talk that much about that, MV, based on the seasonal variability, again, region 3 and region 6 are the best. But the red values show the worst, the least desirable. We don't like small amounts of energy. So region 6 and region 7. So we can say, sorry, Florida and South Carolina, we don't have enough probably comparable amount of energy for installing big facilities in here. But that's just, the same glance. It depends on the type of the instrument that we can install. The new generations of instruments are more optimized and they have lots of more performance than the view. So they could work with smaller amounts of potential energy. So I'm gonna these are the last two slides actually. Spectral partitioning and partition outputs is something that very desirable for this kind of energy characterization. And the concept is, if you see the figure on the left, lower left side of the panel, you see that a 2D spectra, this is the 3D actual representation. has different components, including the wind wave and different systems of swells. These are desirable to be separated, to be used for different design setups of WEC facilities. I'm not going to go through the details here, but I mean, the figure on the right is actually the same concept, but with the numbers in the 2D array of the spectra. So, and I'm going to skip this one and go right to the conclusion. So, so as a summary, we did high resolution models for characterizing wave energy resources with 200 meters along the shoreline. We got the setup, we verified the model using the SWAN unstructured mesh with huge mesh values, and the data that we use, CFSR for wind and wave velocity for the boundary condition. The models were calibrated, verified with all those details that I showed in this presentation. And one good thing about these models was we did those verifications based on the 6 IEC parameters that are exclusively designed for WEC facilities. The white capping parameters actually were kind of localized with this model, calibrated for different ocean basins and different basins, including East Coast and the Gulf Coast. And actually, the results for these 32 years of simulation are already being used for detailed wave energy characterization of these regions. And this is the list of selected list of publications based on this work that you did during these couple of these 6 years. And with that, I finish the presentation, and thank you for attention, and I take questions.
All right, thank you so much, Nabi. That was really interesting, and I appreciate all of the work you do before you run the model to make sure that it's going to give you what you want. So we have plenty of time for questions, and I'll just take my prerogative as the organizer to ask the first one. And I'm not sure if you'll know this, but is it likely that the areas that are most desirable to do wind energy overlap with the areas that would be most desirable to employ wind energy systems?
That's pretty much accurate, yes. Actually, I know that as a fact that people in DOE and Sandia Lab, they are actually working to merge kind of both wind farms and wave farms together, because one thing that they use, I'm not that familiar with this concept, but they lease a part of ocean, from the government. I mean, those companies that the energy company, they lease that part, and they are actually trying to use the best that they could do of that part of the sea. So yeah, merging both of them is a kind of desirable thing that they are doing. Yeah.
Okay, do we have any questions from people online? I see Ardian has a question.
So hello, can you hear me?
Yes, yeah, sure.
Yeah, I have two questions. So it was really interesting to see your work, because this is the same work I did during my undergrad. I was wondering, when you do the long-term simulation like this, did you do like hot and cold start, or you did like every certain period of simulation and doing the
we use hot start, yeah.
Oh, you use hot start.
We ran the model monthly, and we use hot start. And the reason was, I mean, the simulation was losing lots of processors, took like for each month took like 3 or 4 days. So, and it's a big part of that was actually running, writing the outputs because we had a big output mix. But the hard start is the best way to, to keep our data from any interruption or disconnection of the server.
Okay, thank you. So
Sure.
maybe my last question is like, since this is long-term data, have you noticed there is any interdecadal trend? Yeah, interdecadal trend.
You mean with sharing the data?
Yeah, is there any link? With the wave trend is linked with interannual or
Right.
interdecadal phenomenon.
I can send you the contact information. I will send it to you, Chris, and you can get it
Sure.
from him. You can email Dr. Vincent Neary, our first author in this presentation. Dr. Vincent Neary, the last author from Sandia National Lab, and they have their own policies for sharing the data, but I think they will be glad to share data with you in case you have any research project or you want to do any further analysis on that.
Okay, thank you.
All right, I think Xiaodong was next.
Okay. Okay, thank you. So my question is that you show the result. I didn't. So have you shown the result for Gulf of Mexico? So where is the greatest wave potential in Gulf of Mexico?
We have
How deep that is? Because the water is pretty shallow.
Sure. Thank you for the questions. We haven't done that yet. We finished the Gulf of Mexico phase just maybe 6 months ago, 6 months or 1 year. Yeah, 1 year to 6 months ago, depends on some logistic things that we were busy. But still, people in Sandia Lab, they are working on this kind of thing. So the result that I showed you, let me see. Yeah, this result, right?
Mm-hmm.
These results are based on the paper that we worked with the Sandia people last year, but they are actually, there was a kind of, this was a teamwork. We were in charge of modeling and 32-year simulation, and they were in charge of doing the characterization. They are still working on the characterization for the Gulf of Mexico.
Oh, okay. Okay, so but that's fine for the East Coast. When you simulate, how close to shore your simulation goes?
I'm not sure about what you're asking. We did. The simulation include the whole East Coast and the offshore.
No, I mean the distance to the coastline. When you're closer to the shore, the wave are breaking. You not very much energy you can use.
Oh, closer to shore, right?
Yeah.
Closer to shore, yeah. We are not getting close to the safe zone. So if you see this figure, the closest that we got is 5 kilometers. You see?
Which figure I need to see? Figure A, B, C, D, or which one I need?
No. If you look at panel B or C, we have in the legend we have 3 different distances.
That's the distance to the shore.
Yeah,
okay.
distance from the shoreline. Yeah.
Distance from the shoreline. Okay,
Shoreline,
5 kilometers.
5 kilometers. So we are pretty much safe from, because there is a reason for that. Because water depth is a kind of important thing. The wet facilities can be very large. Let me go to the figure. All right, here on the lower left panel, it could be as large as 40 meters, the height, the wet facility. I don't say that all of them are this large, but this model is a large one. So, but at least we are talking about something like 10 to 15 meters. 10 to 15 meters, we need, as in this figure actually specified, the upper panel, depths between 40 meter to 100 meter. That is definitely out of the safe zone and doesn't make any problem.
Mm-hmm. Okay. Okay, so that is dictated by this converter, the instrument. So you have to, the depth has to be certain depth to use this.
Yeah.
Okay.
There is, all of these 6 parameters they put them together with the depth data, and then they decide about that. Those kind of tables that I showed you at last, based on the East Coast, those tables will help together with the depth to how to decide about specific. So, at this time, as much as I know, let's see. This area off the Cape Hatteras and along the coast of Virginia. Oh, let me go to that figure. Actually, region 5. Region 5 is the most favorite zone for the developers and decision makers. Region 5, sorry. Region 5, ER5. That includes part of Virginia and North Carolina coast, including Cape Hatteras.
Okay. Okay, I got you. Okay, thank you.
Sure.
All right, we're at the hour, but if people are happy to stay on a little longer, there's a few more questions. Martin, do you want to ask your question?
Sure. Thanks for your great talk. I was just wondering, have you looked at sort of a coupling between surface waves and surface currents, for example, due to the Gulf Stream?
The best question ever.
Does it have also an effect on your model data comparison?
Yeah. So this part of the project, actually, this phases that we started at the beginning, we were not supposed to include the effect of ocean currents. But these ocean currents, as you mentioned, they could be important, especially on the East Coast because of the Gulf Stream. And the Gulf, in the Gulf of Mexico, I'm not sure about that because the loop current effect can kind of dissipate when we close. It's not very close to the shoreline. It's in the middle of the Gulf of Mexico. But I think this, including the ocean current in our simulation, we are talking about that with the Sandia lab as the next phase, maybe for the East Coast. So to do that, we are actually doing some pilot simulations based on idealized model. If you like that, to see how it works, I had a presentation back in February in Ocean Science meeting in February, and that was in the energy session. And it was actually, the topic was the effect of the Gulf Stream on wave energy characterization. It was based on idealized model. So that's the first part of this. The new thing that we are talking about. Maybe in near future we start realistic models for that.
Yeah, thanks.
Sure.
All right, next, Hafiz.
Hi, can you hear me?
Yep.
Yeah. So thanks for the presentation. I'm just considering the amount of energy consumed in the United States. So I noticed that I think around the first or the first 5 slides, you showed the energy converters, like the size, almost 700 meter. So I'm just wondering, like the amount of converters that will be required in terms of meeting the energy needs of the United States. Do you also consider that?
So you mean this one?
Yeah. So I'm just like, it's just like a general question about like considering the amount of energy that is utilized in the United States in terms of energy consumption. And I know that the main aim of this project is to kind of shift towards renewable energy in terms of meeting the energy needs of the United States, right? So looking at those demands for energy.
NIT, you mean?
Yeah, so I'm just wondering the amount of like wave energy converters that would be installed in terms of meeting the energy needs.
Oh, well, I'm not sure about that. This is something that the decision maker should think about that. I mean, I understand that. I understand about the demand and the amount of that is required for each area, but I'm not
Exactly.
sure how they are going to. It depends on the cost, depends on the different, parameters to decide about that.
Okay, and my second question is this: when you did the sensitivity test, you showed that like one works better, the Johnson, during extreme events and the other during cold fronts. And you briefly made mention about the seasonality of the amount of energy that could be generated from those spots. So, in terms of the sensitivity analysis, do you consider like, or do the amount of energy vary from one spot to another? Like if you have certain amount of energy that could be retrieved from a particular spot at a particular time of the year, as seen in your presentation, does it vary from one spot to another? Like if it is kind of low in this spot for this particular season, then in the next season, like is it higher? So do you also consider that kind of variability with locations and with seasons?
Yeah. Well, as I mentioned here, for example, in this area, in the Gulf of Mexico or in the Caribbean uh, area, we have different atmospheric features, cold fronts and hurricanes, and also fair weather conditions. So we used 4 different. I didn't mention that in the presentation, but for verification and then later calibration. For sensitivity analysis, we use 4 different time periods. 2 time periods were included 4 different hurricanes, and 2 time periods were for cold fronts. Also, sorry, that cold front and also fair weather conditions. So that's why we got different calibration parameters for white capping during the hurricane time and during cold front time. So that was actually considered in our modeling.
So you are saying that those spots that you showed last, that they have like the highest amount of energy. So it is kind of constant throughout the year. Like they are the locations with the highest amount of energy that could be extracted throughout the year. Like they have the maximum amount of energy that could be extracted throughout the year when compared to
In
other
terms of
regions.
energy, we should wait for the characterization results to come. I'm not sure about that, but probably they will have their own classification based on the season. Maybe they have to, in addition to the locality, they need to consider the seasonality and say this season the classification is different from this season.
Okay. And my last question is this: do you also consider that the farther away you move from the coast, as someone once asked, the larger the cost in terms of transporting the energy back if those converters were installed?
No, we didn't consider that one. No.
Okay, thank you.
All right, I think that's it for questions. So everybody can thank Nabi for a great talk, and thanks for sharing with us. And yeah, I'm sure if anybody wants to get in touch with him, you could email him directly or go through me, and we'll look forward to seeing those Gulf of Mexico results coming out.
Sure. Thank you very much. Again, thank you all people for attending and your great questions. And yeah, it was a good opportunity again. All right. Have
All
a
right.
great rest of the day.
You
So
too. Yeah, it
should
was nice
I-
meeting you.
Yeah, sure. Bye.
All right. Bye.